All right, this is kind of the end of lesson 9.1 and lesson 9.2 for my grade 12 40S pre-cal students. So the last couple of days, what we've done is we've been graphing rational functions, and we've been often, go back to a couple of examples here, like for example, I guess I got to go back to the first part of 9.1. Like for example, these guys here that we did in class the other day, we had to long divide to figure out the horizontal asymptotes. Because what we know is, let me go back to this page here. And you don't have to write this down, I'll just do this as some scrap thinking. What we know that is that if we can see a graph that looks like this, oh, no problem, I know it's, one arm up here, one arm down there, I know its shape. If I see a graph like this, oh, no problem for that too. I know that both arms are up here. It's the volcano graph, as they say. So if there is a constant here or a constant here, that constant is going to be my horizontal asymptote. Because think about it, no matter what x is, 1 divided by x could never be 0. So if this thing can never be 0, y could never equal c, whether it's this case or this case. So that's why we did long dividing. I got good news for you. I got a shortcut for that. So the shortcut, hang on a sec, there we go. The shortcut, if you take a look at the top of the page here, is notice that if I were to divide this denominator into this numerator, I'd end up with how many 6's go into 3, which is a half. So the constant part of my answer would be a half. So I already know my vertical asymptote, my horizontal asymptote will be a half. But the shortcut to remember is if the degree of the numerator and the degree of the denominator are equal to each other, notice they're both x squareds, then the leading coefficients as a ratio, which in this case would be the leading coefficient of 3 over 6, that's my horizontal asymptote. So 3 over 6, of course, I can simplify to 1/2. So there we go. That saved us having to do the actual divide. If we'd have done the divide, we'd have had 1/2 on top. But that's just a nice quick way to do it when you're doing your homework. Now you got to be careful with this rule. Like every rule, if you memorize it, no matter how well you memorize it, if you apply it incorrectly, it doesn't work. A lot of people go, oh, that's easy. Take the first thing and the first thing and divide them. So that's 7 over 1. My asymptote's 7. No, it isn't. It's for the leading coefficient of the degree that's the highest. This is degree 3. This is degree 3. Those kind of have to count first. So the equation of the asymptote here is the leading coefficient's -2 on the top and 1 on the bottom. So that's actually going to be y equals -2. Put this into a form where I can write on it better. There we go. So that's y equals -2. Now, this trick only works when the degree on top and the degree on bottom are the same. If the degree of the numerator is smaller than the degree of the denominator, notice this has just a constant and that has an x squared, then the horizontal asymptote is always just 0. And again, you can kind of see that, right? Y could be any number you want except 0, because 1 divided by anything can't be 0. So that's y equals 0. And here, again, this one's maybe a little harder to see why this is true. But the rule works on this one, so it has to work on that one because they have the similar characteristic of the numerator has a smaller degree than the denominator, right? This one's only an x to the power of 1, this one's an x to the power of 3. So once again, the equation of the horizontal asymptote here is y equals 0. There is a more grown-up way of showing why this particular set of shortcuts works, and I'll show it to you in a minute. But here's the third situation. So this is where the degrees are the same. This is where the degree in the denominator is bigger. What if the degree in the numerator is bigger? Then there's actually no restrictions on what y can be. So there is no horizontal asymptote. So in this case, x is bigger than x to the power of 1 is a higher degree than x to the power of 0, and x to the power of 4 is a higher degree than x to the power of 2. So in both cases, there is no horizontal asymptote. So why does this trick work? It's complicated, but not that complicated. Let me just move over for a sec here. You don't have to write this down. We've had this conversation before. What do we have to do here to add those together? Well, we need a common denominator. How do you get it? And very often people say, oh, I multiply the left fraction by 3 and the right fraction by 2. No, you don't. You multiply both fractions by what? By 1. It's the power of 1. I multiply this fraction by 3 over 3, which is just 1. I multiply this fraction by 2 over 2, which is just 1, and then I move on with my life. Remember in grade 10, you were taught how to rationalize denominators. Why, what, and how do you do it? Well, you do it by multiplying by 1. So the property of 1 is what allows us to do all kinds of interesting things in math. You've even seen it in more complex versions of this. Suppose you had to rationalize this denominator. Do you remember how to do it? You'd multiply by the conjugate, but you have to, again, turn that conjugate into a 1 to make it work. So if that method makes sense to you, that's actually what happens here. Here, let's do the first one over here. If I wanted to know what the horizontal asymptote of this is, 3x squared plus 4 over 6x squared plus 8. I again use this trick of multiplying by 1. Oh, is it a subtract on the bottom? Yeah, you're right, it is. Oops, I erased more than I needed to. There we go. So once again, I use the multiply by 1 trick, but here's what my 1 looks like. My 1 looks like this. That's 1, right? It's a number divided by itself. But if I multiply this numerator by 1 over x squared, I get this. And if I multiply the denominator by 1 over x squared, I get this. And that leads me to 3 plus 4 over x squared, and then 6 minus 8 over x squared. And you might be wondering, how on earth does that equal a half when you have all this stuff here that you got to deal with? Well, you now imagine what happens to this equation as you go forever to the left or right. In other words, what happens is if x gets bigger and bigger, what if x is 10 or 100 or 1,000,000 or 1,000,000,000 or 10 billion or 100 billion? What does this number do as x gets bigger forever? It goes to 0. So you can treat these numbers here, they behave like 0 as x gets infinitely big or infinitely small. So if those things are just zeros, y is just 3 over 6, which is a half. And that method works for all of the shortcuts. So let's try another one. Let's try one from the second one. What happens when the bottom is a different degree than the top? So y equals 1 over x squared plus 1. So y equals 1 over x squared plus 1. So I'm going to times by 1 over x squared, because that's the highest degree I have in my question. And that's going to be 1 over x squared. And then I'm going to have x squared over x squared plus 1 over x squared. And then imagine what happens here. I guess these can cancel. I guess I could do one quick simplification here. All right, what happens now as x, again, approaches either positive or negative infinity? What happens to this thing? Well, this fraction becomes so small that it basically becomes 0. So I end up with 0 over 1 plus 0. And like it said in the rule, anytime the numerator has a smaller degree than the denominator, you end up with y equals 0. The technical name for what I'm doing is I'm exploring the limit as x approaches infinity for the function that I'm looking at. What does this function behave like if the x variable in it gets so big or so small that it's basically heading to positive or negative infinity? And that's kind of the first thing you do in calculus. If you take a calculus course, the first unit will always be exploring limits. All right, and I promised you there's a third rule. What if the degree of the numerator is greater than the degree of the denominator? There is no horizontal asymptote, and that's because, okay, what was the question again? It was x plus 9 over 3. And again, okay, so what's the biggest degree here? The biggest degree here is x. So here's my 1 times by that, and I get x over x plus 9 over x all over 3 over x. That's just a 1, right? So I now have 1 plus 9 over x and 3 over x. What happens as this x blows up? It becomes a billion, a trillion, a quadrillion. I get 9 over a quadrillion. That's decimal 0, 0, 0, 0. It's nothing. So this is 1 plus 0. Uh-oh. The denominator becomes 0 too. And of course, that's non-permissible. Therefore, no asymptote exists. So that's where the rule comes from. But if you just want to remember the rule, no problem. So that will save you as you're doing your homework on doing like a long divide or a synthetic divide on every single question, right? Some questions where you don't even have to graph it. You just have to go, oh, what's the asymptotes? If I don't need to actually make a graph, I just need to know what the asymptotes are. These rules will do the trick. All I have to do is go, if the degree on the top is the same as the bottom, just take the 2 leading coefficients, and that's my equation. If the numerator has a smaller degree than the denominator, the rule is it's just 0. And if the numerator has a bigger degree than the denominator, there isn't a horizontal asymptote. All right, quick summary of the basic shapes for those that we actually do have to find the graph of. Anything that's a 1 over x is what we call a split, where there's one arm in one quadrant, usually quadrant 1, and the other arm in quadrant 3. The volcano, where one arm's in quadrant 1 and the other arm's in quadrant 2. I don't like the way I graphed that one. I tried it again. There we go. Then, what if the denominator is a quadratic that's a little more complicated? This one's the driveway. What makes it the driveway is that it has 2 non-permissible values. So if it has 2 non-permissible values, those non-permissible values make asymptotes, and you have the driveway. We've seen that in yesterday's. Something like that. Okay, and then what if there are no non-permissible values in my denominator that's a quadratic? Then the basic shape is always the speed bump. And I can figure out the y-intercept here. Actually, now that I think about it, I don't want to do that. The y-intercept here is where x is 0, so that's going to be 1/9. So I'll make that 1, so 1/9 is like way down here, so it's something like that. Where that's y equals 1/9. Right? There's nothing x can't be, because the only way to make a divide by 0 would be if x squared was somehow -9, and we can't do that with real numbers. So there's a quick summary of 9.1, as well as a shortcut for how to find horizontal asymptotes. That's handy stuff. Let's move on to some more complicated analysis. So that's your homework page. I'll leave you to do work on that. There's the answer key for it. And now we move on to a little tougher analyzing. So let's start with, actually I'm going to start with the second one. Skip this page, and let's look at that one. We're going to sketch that graph. All right, well, we can use our new rule, right? What was the rule again? We know that we have a horizontal asymptote of what? If the numerator has a higher degree than the denominator, what is the horizontal asymptote? Let's see, let's go back to the rule again. What was the rule again? Which rule are we? Rule 1, Rule 2, or Rule 3? Rule 1, the degrees are the same. Rule 2, the denominator is bigger. Rule 3, the numerator is bigger. So which one do we have here again? There we go. So numerator is bigger. So what does that mean? So that's the 0, right? So that's going to be a 0. Okay? So we have a horizontal asymptote of y equals 0. Do we have a vertical asymptote? Well, you might be going, yeah, it's x equals 2. But hold on a sec. Are you sure x can't be 2? Because I can show you something here. Did you notice that if we factor this thing on top, what two numbers times to make 6 and add to make -5? No, I want to rethink that. They add, it's got to be -3 and -2. Hey, look at that. Junk, junk. So y equals x, oops, hang on, just wrote that wrong. Y equals x minus 3. Why would I have an asymptote? This thing should behave exactly like y equals x minus 3, right? This is equivalent to that. They should be the same graph. You know what? I think I'm going to explore that. I'm going to go over to Desmos here. I think I have a Desmos open. I do. Let's just make sure that we're right about this. So there's the graph. Yeah, that looks like a linear line. It looks completely like the line y equals x minus 3, right? Here, let me move that up. There we go. It's black, it's red. It's the same line. It's exactly the same line. Well, actually it's not. It looks like the same line, doesn't it? But check this out. Let's see if I can make this happen. On the black line, when x is -2, you get -5, which is what you'd expect, right? Plug -2 in for x, and -2 minus 3 is -5. Right there. But if I did the same thing on the red line, what happens at -2? Oh, sorry, is it 2? Oh, I meant 2. Thank you. You're right. I'm on the wrong place. What happens at 2? There we go. 2. There. Can you see that? Let me again show you the black one. Black one won't do that. At x equals 2, no problem. I used the wrong point. Sorry about that. 2 makes -1. When you plug in a 2 here, 2 minus 3 is -1. There it is. But when I plug 2 into that function there, it tells me, hey, you can't divide by 0. So we have ourselves a new feature here. It's not really an asymptote, right? As I get infinitely close to that point, is it shooting up or down forever, like the arms of an asymptote do? No. It's just a hole. So that's the way we have to deal with that. We have to realize that we have a situation where we have a hole. Okay, let me go back to the first one. I'll finish this one off in a minute. Go back a page now. So if we're going to sketch this graph, factor the numerator and denominator. So the denominator factors, and check it out, the denominator has the same factor as the numerator. It has an x plus 1. So x equals -1 is a non-permissible value. But this graph here should be identical to this graph, except this graph has no problem letting x be -1. I'd get 1 over -4. Whereas my original graph, because of this factor here, it can't be -1. So we have what's called a point of discontinuity. A point of discontinuity is a point at which the graph of a function is not continuous. This point is missing from the graph. We represent it with a little open circle. Points of discontinuity are often called holes. You've seen this before, using open circles to represent numbers that don't exist. Remember in grade 9, graphing what that looks like? You'd go 1, 2, 3, you'd put a solid dot and an arrow. But if you were to graph x is greater than 3 without the equals, do you remember how you did that? You used an open circle to show that x can't actually exist at 3 because it has to be bigger. Remember that? Same exact logic here. Instead of trying to graph this thing, which I just look at and go, I don't know what shape that is. Once I simplify it to this, I go, oh, I know what that is. It's the graph y equals 1 over x shifted 3 units to the right. And I know that it still does have an asymptote at 3. So let's put the asymptote at 3 down. Let me make that a little smaller so it fits on the screen. There we go. So we have an asymptote at 3. Right? Okay. And we can do all the usual bells and whistles. So this is, again, we're actually graphing y equals, what are we graphing here? X plus 1 over x squared minus 2x minus 3. But this thing looks just like, looks exactly like y equals 1 over x minus 3 with a discontinuity at x equals, what was it? X equals -1. Okay, so what are my other things I can do to make this graph? So y equals 1 over x minus 3. Let's do the other stuff we did yesterday and the day before to graph this thing. What's its x-intercept? The x-intercept happens when y is 0. 0 is equal to 1. Oh, yeah, that's right. We can't have that. That's an asymptote. I forgot. Horizontal asymptote. At 0. We already knew that. What is, so none. What is the y-intercept? Let's find a y-intercept. That'd be helpful. Y-intercept happens when x is 0. So when x is 0, I get y equals 1 over 0 minus 3. So that's -1/3. Okay, so the y-intercept's -1/3, so maybe about there. I know that there's no stretch happening to this thing, so I know that that would be a point. That would be a point. But, oh, wait a minute. X is equal to -1 is going to have a hole in it. Now, where is that hole exactly? If I go to this thing here and substitute in x is -1, I get 1 over -1 minus 3, so I get 1 over -4. So the point -1, -1/4 is the hole in this graph. So let's put that onto the graph. So try to estimate whereabouts 1/4 is. Maybe that's a little too high still, eh? If that dot there was 1/3, this has to be up a little. There we go. And that's it. That's my graph. I know that arm goes that way. Something like that. And this arm goes this way. And there's my graph. That there is the hole that we do not fill in. Let me see if I can make it better than that. Make it a little bigger, perhaps. There we go. Something like that. There we have it. Okay, let's finish off the second one now. We already kind of got it started. We know we have a horizontal asymptote of y is 0 again. We know that it's going to behave just like y equals x minus 3, which is a straight line. That's easy to graph. But it does have a hole. It has a discontinuity at x equals 2. So what's the y coordinate of that? If x was 2, I'd have 2 minus 3, which is negative 1. So my discontinuity is the point. So hole at 2, negative 1. So let's do all the other data on this thing. Can I move the screen here? Okay, so non-permissible value. So my non-permissible value is x equals 2. I have an x-intercept. Oh, I haven't figured out the x-intercept yet. Go back to the original equation for the x-intercept. So the x-intercept, I'll do that over here. X-intercepts happen when y is 0. And when y is 0, the denominator just goes away. Okay, so let's see. I have x-intercepts there at, x would be minus 3 and x would be minus 2. But, oh yeah, wait a minute. This is not a permissible value. X can't be 2, so I really only have an x-intercept at 3, right? Because that one's my non-permissible value. So x equals 3 is my x-intercept. 3. What about my y-intercept? Well, let's see. Let's go to the original equation again. The y-intercept happens where x is 0, so that'd be 0 squared minus 5 times 0 plus 6 over 0 minus 2, which is 6 over negative 2, which is negative 3. So I have a y-intercept of negative 3. Would I have gotten the same intercepts if I'd have used the simplified version of the equation? Right? The original equation was this guy here with this big divide, but I realized that it actually is the same as this equation except for the hole. So as long as I'm not looking for where the intercept is and that happens to be the hole, again, what happens? Let's find the x and y intercepts here. So what's the x-intercept on this guy? X-intercept happens when y is 0. 0 equals x minus 3. Oh yeah, x equals 3. Let's find the y-intercept. Do we get the same thing that we did in this one? We should. What happens when x is 0? Negative 3. So yeah, from now on, as long as the non-permissible value isn't an intercept, we could just use the simplified version of the equation. So there we go. We have our x and y intercepts at 3 and negative 3. Vertical asymptote, we don't have any. Horizontal asymptote, we don't have any. Point of discontinuity, that's our hole at 2, negative 1. Domain, well, I can say x can be anything except 2. So I can go from negative infinity to 2, and then 2 to infinity. And for range, well, y can be anything except this negative 1. So I can go from negative infinity to negative 1, and then from negative 1 up to infinity. So at negative 1 for y, and 2, so 2, negative 1. Okay, I've exaggerated a little, but there it is. There's the hole, the discontinuity. Otherwise, this just looks like a straight line. All right, explain the end behavior near the non-permissible value. Well, unlike asymptotes, whereas you get closer to the asymptote, you either head up to positive infinity or you head down to negative infinity. As you get closer and closer and closer to this hole that doesn't exist, you get closer and closer and closer to the y value of negative 1. So as x approaches 2, y approaches negative 1. The end behavior of the graph, as x approaches positive infinity, so does y, right? As x goes up forever, y goes up forever. And as y goes down, or whoops, other way around, as x goes down forever, y goes down forever. All right, let's try another one. Let's take a look at this guy. What do we know about this thing? Well, I think the first thing I'm going to try to do is factor it. How's your factoring skills, guys? Bottom one's easy. Let's do the bottom one first. What two numbers times to make 2 add to make negative 3? It's going to be negative 2 and negative 1, right? Top's a little harder. 2x squared can really only be broken into 2x and x. But this negative 2 could be negative 2 on this side and 1 on that side, 1 on the left, negative 2 on the right. Which one does it have to be? Well, I have to get to negative 3. So just by kind of juggling it, I can logically reason out that that's the way it has to work. So there's my factoring skills coming back. And now those two cancel each other out. So this thing simplifies to that. But remember, I have a discontinuity when x is equal to 2, right? Even though this thing canceled, at the original equation, if you plugged in 2, you'd get divide by 0, and you can't do that. So you have a discontinuity when x is 2. Let's figure out how much that is, though. If x is 2, where is the whole? That's 2 times 2 plus 1 over 2 minus 1. So that's 4 plus 1, that's 5 over 1. So the discontinuity is the point 2, 5. So that's where the hole is when I draw my graph. Otherwise, we have to figure out all the other stuff about this graph. What kind of a thing is it? Well, it's a 1 over x graph that's been transformed. Let's figure out what the transformations are. Let's long divide it. Y'all can synthetically divide if you want to. Oops. Oh, I accidentally hit the erase button. There we go. So x plus minus 1 goes into here, so x goes into 2x twice. 1 minus negative 2, that's 3. So that means that the actual graph, instead of this equation, I can write this equation. It's plus 2, and the 3 is the remainder. So there we go. Okay, I also could have gotten this same horizontal asymptote by just going that's 2 over 1 using my shortcut, but I kind of wanted to see what this graph was anyway because I had to sketch it. So my horizontal asymptote is y equals 2. My vertical asymptote is x equals 1. That 3 is a stretch, just to keep in mind. Let's find the x and y intercepts. My x-intercept, and we just figured out on the last example that we can use our simplified version to do that. So the x-intercept happens when y is 0. So doing a little bit of algebra, the 2 becomes negative when it goes to the other side. Should have given myself more room to do this. So that's going to be negative 2x plus 2 equals 3. So negative 2x is equal to 1. So x is equal to negative 1/2. Somebody double check my algebra, make sure I didn't goof that up. And my y-intercept, that's when x is 0. So that's 3 divided by negative 1, so that's negative 3 plus 2, which is negative 1. All right, so I think I'm ready to get started now. So I have two non-permissible values. At x is 2, and y, that was right there, and y is 1. Sorry, and x is 1, right there. But not both of them did not get to be asymptotes. My vertical asymptote is the x equals 1. The x equals 2 is my point of discontinuity. And what was the coordinate for the y again? We found it. I remember finding it. There it is, 2, 5. All right, we found the intercepts. X was -0.5. Y was -1. Horizontal asymptote we found. Y is equal to 2. I think I'm ready to graph this thing. So let's see. My vertical asymptote is 1. So there we go. My horizontal asymptote is 2. I have a y-intercept of -1. I have an x-intercept of -0.5. Oh, it's another one of those situations where both of the intercepts are on one arm. I'd kind of like a point in the other arm. What's the other way I could find points again? I could do mapping, right? I go back to this equation here. And let's pick the point 1, 1 and map it so that we have another point to play with. So where does the point 1, 1 end up? What's the three things happening to 1, 1? What does this 3 do? It times the y values by 3. What does this 1 do? Moves us 1 unit to the right. What does this 2 do? Moves us 2 units up. 2, 5. Oh, wait a minute. 2, 5 is my hole. I already knew that point. 2, 5 is the hole. Oh, well. So it goes. I could draw that better. I want to center that right on there. All right, let's pick a different point then. What's another point that would have been on the same arm? How about the point 2, 1/2? Let's see where that goes. Okay, where's 2, 1/2 going to end up? Or actually, I got a better idea. I don't want to be up here because I'm out of grid. I got a better idea. Let's do 1/2, 2. There, that'll be below that hole that I just drew. All right, let's run through the points again. Times the y values by 3. Oh, that's not going to work, is it? That's still going to end up way above here, isn't it? Yeah, it is. Okay, mulligan. I think I'm going to go back to the other one. 1/2, 2. So that's still not going to work, is it? Let's do that one. So let's multiply the y values by 3. If we multiply y values by 3, we get 3/2. Then if we take this 1 and move 1 to the right, we get that. And then if we move 2 up, 3/2 plus 4/2 is 7/2, which is the same as 3.5. So 3, 3.5. That'll be my other point. 3, 1, 2, 3.5. Okay, I'm ready to draw now. This arm is going to do this. And this arm down here is going to do this. Something like that. Let me make that a bit smaller. There we go. All right. Oh, I guess I didn't answer my domain and range. What's the domain and what's the range? Well, x, there's two numbers x can't touch. So I can go from -infinity up to 1. Then I can go from 1 to 2. Then I can go from 2 to infinity. For the range, there's two numbers that y can't touch. Y can't touch 5 and 2. So I can go from -infinity to 2. I can go from 2 to 5. And then I can go from 5 to infinity. For once, it might actually have been easier to do these in set notation. In set notation, I could have just said domain is x cannot equal 1 and 2, but it can be anything else. That was probably simpler. I have a question. Yep. Sure. The question is, couldn't we have just like flipped points from the ones that we knew down here? That's what you mean, right? Because you know they have to be symmetrical? Yes. So the question was, instead of going through all this mapping nonsense, which I had to kind of think about, couldn't I have just taken these 2 points here that I know exist and then find their analogs by symmetry up here? And actually, yeah, that works. But the reason why, if this was a test and it was worth marks and stuff, by doing the mapping, if I had somehow graphed these points wrong, I would then just reflect them wrong, or I would, by symmetry, put them wrong on top. Whereas as long as I do my arithmetic right, the mapping will work out. So this actually acts as like a little check to make sure I'm doing it right, which is one of the reasons why I like doing it that way. But yep, you are 100% correct. You could just take these 2 points and find them up there. Looks like we actually already have one. Isn't this the same? Oh no, not quite. Yeah, this actually is the same point as that, isn't it? Symmetrically. Yeah. So yes, you could do it that way. Good question. All right, check out C. What are we going to do with that guy? Oh, right. So explain the behavior of the graph near the non-permissible values. Okay, well, all right. They don't give me a whole lot of room to do this. I'll do it down here. As x approaches, okay, so the first one is the asymptote. As x approaches 1 from the left, y goes to negative infinity. As x approaches 1 from the right, y goes to positive infinity, right? Because it goes down forever, up forever. The other non-permissible value, as x approaches 2 from either direction, or is it 2? Yeah, it's 2. As x approaches 2 from either direction, if it's behaving the same in both directions, coming from the left or coming from the right, I'm heading towards y is 5. So I don't have to say from the left or right if it's the same. So as x approaches 2, y approaches 5. So there we go. So that's the near the non-permissible values behavior. The end behavior, as x gets bigger forever, what's y doing? Y is approaching, and actually I could say again, it's the same in both directions. So I'll say plus or minus infinity. Whether I'm going forever that way or forever that way, what's y doing? It's approaching, isn't it 2? It's approaching 2, right? Because that's the asymptote. It's getting infinitely close to 2, but it'll never touch it. So there we go. So that's my end behavior. Question? We might. These make for great multiple choice questions too, right? Give you an equation. And the end behavior of this is, and then we can mix up the numbers and stuff. Yep. No, end behavior means as you like head forever to the left or forever to the right. So around the hole, it doesn't really matter. Like we describe the hole right here. This is the behavior around the non-permissible value of 2, right? Is that your question? Yeah. You don't need to worry about end behavior around an asymptote or a discontinuity. That's just what happens if you go forever to the left, forever to the right. Okay, so there we go. That's, let me get rid of the highlighting. That takes us to C. Okay, what can I do with that thing? Well, same thing. The rules don't change because the question looks weirder. I factor. And on the bottom, I can factor out an x. So I have that, which simplifies to this. Okay. I honestly don't know what this looks like. Does it have a parent function of this? No. Does it have a parent function like that? No. It's not a split. It's not a volcano. It's not a speed bump. It's not a driveway. I have to rely on my tests to figure out what this thing is doing. So I think the first test I'm going to do is divide. So I'm going to long divide this. How many x minus 4s go into x? Well, one of them does. 1 times x minus 4 is x minus 4. When I subtract that, I have a remainder of 4. So I can rewrite this equation as my remainder of 4 over my divisor plus my quotient. Oh, it is a split graph, so it is one like that. Now I see what it is. Okay, so what do I know just by looking at all of this? Well, let's keep track of everything. There's a lot to keep track of here. How about we keep track of what we did up here first? What did we do when we went from this step to this step? I divided x by itself, right? I canceled an x. But that took away a non-permissible value, right? I had 2 non-permissible values when I started before that cancel. The non-permissible values are obviously x cannot equal 4. And what's the other one? 0. So the 0 one got canceled away. So it's not an asymptote. It is a discontinuity. So I have a discontinuity when x is 0, and you can just go back to the original one. X is 0 is a discontinuity. But if I go to this one here and plug in 0, I'd get 4. I'll do this in scrap paper. 4 over 0 minus 4 plus 1. 4 over negative 4 is negative 1. Oh, the discontinuity happens at 0, 0, because that's going to be 0. All right, so I have a hole at 0, 0. What else do I have? I have a horizontal asymptote of 1. I have a vertical asymptote of 4. Should we find some intercepts? Let's find the x-intercept first. What's the x-intercept? If y is 0, I have 0 equals 4 over x minus 4 plus 1, which would be negative 1 is equal to 4 over x minus 4, times both sides of the equation by x minus 4. That gives me negative x plus 4 equals 4. And my x-intercept, oh yeah, I kind of already knew this if I look over here. The x-intercept is 0, 0, and I already know that that's a hole. So in other words, my x-intercept is the discontinuity. Okay, I've kind of run out of room, sorry. Hope you can write smaller or maybe supplement with some loose leaf or something. Can I find a y-intercept? Let's find a y-intercept. Y-intercepts happen to this equation here when x is 0. And, we kind of already know this too. This is also 0. So that's it. It goes through 0, 0. And it's a hole. That's all I know so far. And I know that at y is equal to 1, I have a horizontal asymptote. And at x equals 4, I have a vertical asymptote. And that's about it. So let's fill in our chart. Our non-permissible values are 0 and 4. Our x-intercept, well, we don't really have one because it's a hole. So I'll say I don't have one. Same thing with the y-intercept. My vertical asymptote is x equals 4. My horizontal asymptote is y equals 1. My point of discontinuity is 0, 0. And I know that I have two arms. One's over here someplace and the other's over there someplace. I might plug in a couple of values and map them to get some more points. But I'm just going to make a sketch on this one. So it's going to, I know how it behaves as it heads towards asymptotes. It's going to do something like that. And then up here, the same. Okay, if I wanted it to be more accurate, I'd have to get more points. And for my domain, I think I'll do this one in set notation. It's actually less writing this time. So x can't equal 0 and 4, but it can be everything else. And range, y can't equal 0 and 1, but it can be anything else. And there we go. Your turn to try some. So the next page is a homework page based on this, and I have an extra page of practice that I'll come around and I'll hand out in a couple minutes. And I'm going to let you have tomorrow as basically a work period, because notice how long each question takes. Like, you have to do all these tests, do all this thinking. And can I point out to you that I want you to do this too? If you're stuck, give yourself a hint, and no, don't check the answer key. You want to know how to give yourself a hint? Graph it on Desmos. The actual curriculum does say that students are supposed to actually learn how to use graphing technology in this course, and we don't want to make you buy a $150 graphing calculator. I'm quite happy if you know how to operate Desmos. So actually take a second here. In fact, let's take a look at all the examples we did today. Maybe before we leave them, we got a question though. Question? Yes. That's true. I should be having this conversation with my slot 6 class. That's another reason why I didn't plan a lesson for tomorrow. I didn't want slot 6 to get ahead of you guys. Yeah, there's a lesson there. Okay, actually I can stop the video. Well, no, I guess I can show the video people who might be watching this Desmos, just in case there's still people who've never touched Desmos. Okay, let's go back to Desmos. I think all the examples I did today are on here, on this little graph that I made. So there's the first one we did. Okay, there was the 3 examples we just did. So what did we think this one was? There it is. It has an, let's see, what was the first example again? Let me check my notes. There it is. Okay, yeah, this is it right here, right? X plus 1, isn't that it? Yeah, there it is. Okay, so it had an asymptote at 3. There it is, right? And then it had a discontinuity. Where was the discontinuity? It's at -1. So track your cursor to -1 and you should see a hole. Yep, there it is. And people always ask, why don't they draw the hole all the time, the way that we draw it when we make a sketch? And the answer is, the programmers at Desmos were listening to teachers who said they don't want to be able to just have students not have to try to figure that out for themselves. So that's why you do the homework, figure out where the hole is, and then you can look at Desmos and go, do I have that hole in the right place? Yep, there it is. Undefined at -1. Okay, what was the second example? The second example turned out to be also a split graph, and it had an asymptote at, what was the asymptote for B? The asymptote for B was, hold on, my notes are in the wrong order. The asymptote for B was x equals 1, yep, looks good. If you're not sure, you know what you can do is you can actually graph x equals 1 and then just say, yep, it's not, see, go down forever. Is it touching it? Nope, it's not. So there we go, we got it. And where was the discontinuity for this one? The discontinuity is supposed to be at 2, 5. So look at the point 2, 5, hole, we're good. It doesn't tell you that it's 5 either, it just says undefined. So you have to figure out the 5 for yourself. And then the last one we did was also a split. Lots of splits today. And okay, what did we get? We got an asymptote at, what was the asymptote for the C1? The C1's asymptote, looking back at my notes here, was x equals 4. Yep. Looks like we're getting closer and closer to 4, but we're not touching it. And what was the discontinuity? The discontinuity happened right at 0, 0. Is it a hole? It's a hole. We nailed them. Compare this to our sketch. I think we should be pretty happy. Desmos, sketch. We got this. Okay? So there you go. For your homework, you have to do what I just did. All those little steps, make a sketch. If you get lost, help yourself with Desmos. Sadly, you can't use Desmos on the test, but other than that, it's a very helpful tool for your homework. All right, I'm going to shut my video off now. Thanks for watching.